What does it take to build a truck so large it can carry 500 short tons in a single load? And why would any industry need something that extreme? A machine longer than a city bus, taller than a two-story house, and weighing in at 810 metric tons stands idle in the pale light of a Belarusian morning. The BLA's 75710, first rolled out in 2013, is not a prototype or a one-off experiment. This is a production vehicle, engineered to move more rock in a single load than any truck before it. Its official payload is 450 metric tons, nearly 500 short tons. Each of its 8 tires is 4 meters tall, supporting the weight of a small office building. Two 16-cylinder diesel engines, each producing 2,300 horsepower, work in tandem to generate 4,600 horsepower needed to move this mass up the steep grades of open-pit mines. The numbers sound abstract until you stand beneath it and realize a human barely reaches halfway up the rim. At the rollout, the factory manager stands in the shadow of the truck's massive dump body. He says this is not about breaking records, his voice echoing off steel. He says it is about moving more material, more efficiently, because every minute and every fuel gallon counts in a mine. Every dimension of the 75710, 20.6 meters long, 8.16 meters high, nearly 10 meters wide, reflects a single purpose: to cut the cost per ton moved. The truck's design is dictated by the economics of modern mining, not by spectacle. Tire diameter, axle load, and even the shape of the dump body are all calculated responses to the physics of rolling resistance, the brutal gradients of haul roads, and the relentless pressure to deliver more ore at lower cost. This is where the story begins. Not with a marvel of size for its own sake, but with a machine built to answer the toughest economic questions in mining. If you find these hidden systems as fascinating as we do, subscribe and join the ongoing investigation into the machines that quietly shape our world. In 1957, a team of engineers rolled a machine onto the sand of the Sahara that looked like something from a different planet. The Berliet T100, stretching nearly 12 meters and weighing more than 50 tons empty, was built to haul oil field equipment across vast, roadless deserts. Its secret weapon was a set of balloon-like tires, each over a meter wide, designed to float over soft ground where smaller trucks would sink. But the real struggle was hidden under the hood. Every time the T100 hit a deep drift or tried to pull a full load up a dune, the mechanical gearbox strained under forces it was never built to handle. Early mechanical transmissions simply could not multiply torque fast enough or survive the pounding from loads that neared 100 tons. The T100's designers could make the frame bigger and the tires wider, but they kept running into the same wall: the gearbox. A decade later, engineers in North America took a different approach. In 1973, the Terex 3319 Titan appeared in a Canadian mining pit. This was a truck of unprecedented ambition, 20 meters long, nearly 10 meters wide, and capable of carrying over 300 tons. Instead of relying on a single mechanical transmission, the Titan used a diesel-electric system. Its diesel engine powered a generator, which then sent electricity to massive traction motors at each wheel. This design bypassed the gearbox entirely, delivering torque directly to the axles and allowing the Titan to climb grades with loads that would have destroyed any mechanical drive. The lessons from these prototypes were clear to the engineers who built them. Making a truck bigger was not just a matter of adding steel. It meant rethinking how power moved from engine to wheels, how weight was spread across the ground, and how the laws of physics set hard limits on what could be built. The path from the Berliet T100's sand-bound struggles to the Titan's electric drive laid the groundwork for every ultra-class haul truck that followed. A 450-ton payload means nothing if you cannot get power to the ground. For decades, mechanical gearboxes stood as the barrier. No matter how large the engine, the transmission was always the weak link. Teeth sheared, housings cracked, and heat built up faster than it could be carried away. The leap came with the generator, bus, and motor system, a diesel-electric drive that rewrote the rules for moving mass. Here, the engine's sole job is to spin a generator. Electricity flows through a high-voltage bus, feeding massive traction motors mounted directly at each wheel. Each motor delivers torque with no clutch, no shifting, and no risk of mechanical overload. On the Bell AZ75710, two 16-cylinder diesel engines feed twin alternators, together generating over 4,600 horsepower. That current drives 4 alternating current traction motors, one per axle, each capable of precise, independent torque control. The logic is simple, but the payoff is enormous. Instead of one gearbox straining under a mountain of force, the electric system shares the load across every wheel. When the truck creeps up a 10% grade, the motors provide full pulling power at 0 speed. No gear hunting, no stalling. If a single engine or generator fails, the system can limp home on half power, a level of redundancy mechanical drives cannot match. Thermal management becomes the new frontier. Liquid-cooled motors and resistor grids dissipate the heat from both propulsion and braking, keeping the system within safe limits even during hour-long climbs or descents. A Komatsu engineer puts it this way: with electric drive, you size your system for the force, not the fear of breaking something. This architecture is what lets a machine the size of a house move mountains reliably, predictably, and at a scale that mechanical transmissions could never reach. The diesel-electric solution did not just make bigger trucks possible, it made them practical. A fleet planner staring at the latest production schedule faces a simple but brutal math problem. How much force does it take to move 650,000 kilograms of rock up a 10% grade? The answer is not a guess. It is a calculation that defines the ceiling for every ultra-class truck on Earth. Gravity alone pulls against the loaded Bell AZ757 with a force of over 637,000 newtons when it tackles that slope. Add in rolling resistance from the rough haul road, and the total climbs to nearly 750,000 newtons. To keep the truck moving at even a crawl, the motors must deliver a combined torque of 1.5 million newton meters to the wheels. This is where the numbers become a hard stop. No matter how much horsepower you add, the laws of physics refuse to bend. If you try to haul more than about 450 tons up that grade, torque demand outpaces what even the largest electric motors and generators can provide without overheating or stalling. The result is a numeric boundary. Payload is capped not by what the steel frame can hold, but by what the drive system can push up the hill at a sustainable speed. Every decision in the planner's toolkit, from engine size to number of motors and even the length of the dump body, funnels back to this calculation. It is why the world's biggest trucks all cluster around the same payload range, and why no serious mining operation gambles on a design that cannot conquer the steepest haul road fully loaded. The next constraint waits just beyond the drive motors, the tires themselves. For now, the fleet planner's spreadsheet tells a clear story. Physics, not ambition, draws the line. A 4-meter tire supports more than 100 tons of weight, and yet in the world of ultra-class haul trucks, that number isn't a starting point. It's a ceiling. The tire specialist standing beside a quarry tread nearly twice his height says you can't cheat the rubber. No matter how much steel and horsepower you throw at a truck, the entire load must pass through 8 contact patches, each the size of a small dining table. Push beyond a tire's load rating, about 102 tons for the giant 5980 R63s used on the Bell AZ75710, and the risk isn't just a blowout. Sidewall flex leads to heat buildup, tread delamination, or catastrophic failure that can sideline a $6 million truck for weeks. To distribute the strain, engineers rely on high-drop pneumatic suspension. Nitrogen oil cylinders that dampen shocks and keep axle loads balanced, even as the truck lurches over rutted haul roads. On the Bell AZ 75710, these systems allow for a near-perfect 50-50 weight split between front and rear axles when fully loaded, a feat that lets the truck carry 90 tons more than its closest rivals, but the suspension can only buy so much margin. Every bump, every ton is ultimately transmitted to the tires. Braking brings its own physics lesson. When 810 tons of mass rolls downhill, the energy doesn't vanish. It becomes heat. The dynamic retarder on the Bell AZ 75710 can dissipate up to 4,800 kilowatts, enough to power a small town by turning the traction motors into generators and dumping the energy into resistor grids. Still, the tires and brakes must absorb what's left, and repeated descents can push temperatures into the danger zone. Here, the boundary is absolute. Tire chemistry, suspension stroke, and heat dissipation set the upper limit for how big a truck can get. When engineers run the numbers, they find themselves boxed in not by ambition, but by what the ground, the rubber, and the laws of thermodynamics will allow. In the early 1960s, American engineers set out to answer a problem that seemed unsolvable. How do you haul supplies across hundreds of miles of Arctic wilderness, where roads are buried and the ground itself shifts with the season? Their answer was the Letourneau TC497 overland train, a modular convoy stretching nearly 2 football fields long, each segment powered by its own electric hub motor. At full length, the train could snake over ice and tundra. Its diesel-electric turbines fed electricity down the line to dozens of wheels. But in 1962, during a trial at Camp Tudo in Greenland, the TC497 met the limits of its own ambition. An electrical failure left the entire train stranded for 36 hours in sub-zero temperatures, with no way to move or even heat the cabins. One Cold War engineer summed up the lesson: the bigger you build, the more places it can break. The experiment proved that modular electric drive could in theory conquer any terrain, but in practice, reliability set a hard boundary that no amount of power could overcome. In the Arctic, the ground itself becomes the enemy. Here, trucks like the CAM-AZ 7850 and the Vitiaz DT30 PM face a different kind of challenge, one where tires alone cannot keep a vehicle afloat. The Vitiaz, with its twin articulated tracked modules, spreads its weight so evenly that it can cross bogs, snowfields, and even thin ice without breaking through. Each track acts as a giant snowshoe, keeping ground pressure lower than a human footprint. Meanwhile, the CAM-AZ platform relies on independent suspension and high flotation tires to survive deep ruts and frozen tundra. But when it comes to lifting or hauling on unstable ground, engineers turn to machines like the Liebherr LG 1750. Its rigid frame and modular construction allow it to absorb massive stresses without twisting, a necessity when hoisting hundreds of tons in shifting permafrost. Whether it is the relentless crawl of a tracked carrier or the unyielding stability of a crane, these designs reveal that conquering extreme terrain demands a different answer than simply building bigger. The solution is always governed by the same logic: spread the load, manage the stress, and let the ground decide the rules. A single line in a planner's spreadsheet can decide the fate of a billion-dollar mine. The formula reads like this: cost per ton equals the sum of fuel, labor, maintenance, and capital expenses, divided by the total tonnage moved over the mine's life. For a project moving 200 million tons of rock, even a small change in this equation can mean a difference measured in tens of millions of dollars. The numbers are stark. If a mine can shave just 60 cents off the cost of moving each ton, that is a savings of $120 million over the project's run. The logic behind ultra-class trucks is as simple as it is relentless. Fewer, bigger trucks mean fewer drivers, less fuel burned per ton, and less time lost to maintenance. A Bell AZ 75710, with its 450-ton payload, can replace 3 smaller trucks in a single trip. That means 1 operator, 1 machine to service, and 1 set of tires to replace, instead of 3. The capital cost for a truck this size is staggering, upwards of $6 million per unit, but the per-ton math justifies the investment when the scale is right. A mine fleet planner puts it plainly: if you can move more rock with fewer machines, you win. But every extra ton comes with new risks. The infrastructure must keep up. Haul roads must be wider and stronger. Maintenance bays need to fit vehicles the size of small buildings, and every breakdown carries a heavier price. Yet for the largest mines, the savings are too big to ignore. The economic rationale for building the world's biggest trucks is not about breaking records. It is about winning a ruthless numbers game where every cent counts and every calculation is a bet on the future. A haul road that can carry 810 tons at speed is not just a stretch of gravel, it is an engineered structure layered with compacted rock and geotextile designed to withstand the relentless pressure of ultra-class trucks. Every pass of a Bell AZ 75710 grinds tens of thousands of kilograms into the roadbed, forcing site managers to reinforce, grade, and repair surfaces constantly. When a truck this size develops a rut, the repair bill can reach 6 figures overnight, and a single collapse may halt production across an entire pit. Maintenance bays, once sized for 150-ton trucks, now resemble aircraft hangars, built to house machines longer than a city bus and tall enough to dwarf the average worker. Overhead cranes, custom jacks, and reinforced floors become standard, not luxury. Yet the most fragile link in this chain is the tire supply. Each 5980 R63 tire, 4 meters tall and weighing more than 5 tons, must be sourced from a handful of specialized factories worldwide. During the 2005 to 2008 tire shortage, global output of these giant tires fell so far behind demand that mines in Australia and Chile lost up to 20% of their output, waiting months for new shipments. Managers recall entire fleets sidelined, trucks cannibalized for spares, and production forecasts shredded by a single missing tire. In a business where every day offline costs hundreds of thousands of dollars, the vulnerability was impossible to ignore. An operations site manager puts it plainly: you can build the biggest truck in the world, but if the road gives way or you run out of tires, it is just a monument to lost time. These moments expose the upper limit of scale, not set by engineering ambition, but by the realities of infrastructure, logistics, and the global supply chain. As mines push for greater efficiency, the search for solutions now turns to autonomy and predictive maintenance, hoping to sidestep the very bottlenecks that once seemed unbreakable. In a control room overlooking the mine, an autonomy engineer scrolls through live fleet data. On the screens, rows of ultra-class trucks move in quiet formation, each guided by a network of sensors, GPS, and remote operators. The shift to semi-autonomous haulage began as a response to 2 relentless pressures: labor costs and safety risk. In Australia's Pilbara region, where Komatsu 980E and Caterpillar 797F trucks have run semi-autonomous for nearly a decade, the numbers are hard to ignore. Accident rates have dropped 80% since the first autonomous units rolled out. The need for on-site drivers has been cut in half. The impact ripples far beyond payroll. Fewer people in the pit means fewer injuries, less downtime for shift changes, and a dramatic drop in human error. Each truck follows an optimized route, braking and accelerating with algorithmic precision, shaving seconds off every cycle and squeezing more tonnage from every hour. When a machine does need intervention, the system reroutes the rest of the fleet in real time, keeping production moving. An autonomy program manager puts it simply: we're not just making trucks bigger, we're making them smarter. For mines pushing millions of tons per year, these gains mean tens of millions saved over a project's life. The economics that once demanded ever larger machines now reward intelligence and coordination. The future of ultra-class haulage is not just about scale, but about fleets that adapt, learn, and deliver more with less risk and less labor. Right now, a single ultra-class haul truck can move nearly 500,000 kilograms in one load because the world's appetite for metals and minerals leaves no room for inefficiency. As global demand accelerates, the size and logic of these machines become a mirror for how we extract value from the Earth itself. The real limit isn't engineering, it's what we're willing to consume. Subscribe to keep uncovering the machinery shaping our world.